ways and how we use all the tools that are available at HRSC to generate a safe and predictable remediation. Today, we will cover the injection part and how we apply amendments and solids into the ground and the experience that we learned over 20 years of applications. Today, I'm joined by Mike Mazaris at AST Environmental, who will support me in sharing some of the experience we have at a global level. And that's what we will cover today. So we will give you an insight on why we selected activated carbon as one of our main, let's say, products to support our remediation efforts, and why slurries, and how we select the correct approach and technique when it comes to the installation, and same as last time, leave time for a Q&A session. To submit questions, you're more than welcome to do so by clicking at the bottom of your screen. You can select the Q&A chat box, and you can just file in your questions, and we will go through at the end of the presentation. Said so, I'd like to leave the word to Mike to introduce himself and our group and how we got here today.
Sure.
Thank you, Mike.
Thank you, Giorgio. Can you hear me?
Yes.
Okay, great. Thank you. Good afternoon, everyone. I'm joining you from Denver, Colorado, which is where I'm based. And so AST is the part of RPI group as well as Ejlskov, and we are tasked by RPI to help evaluate sites and work with our partner companies like Ejlskov and in other countries around the world to be able to come up with a proper design, proper characterization, which was which we covered in the previous webinar, which has been recorded, if you're interested, and to be able to develop a design. And big piece of that is the application, which is the focus of the webinar today. And so AST, we started injecting slurries more than 15 years ago with RPI, mainly on the eastern coast of the United States. And this is primarily the Boss 200 and Boss 100 products, which have been out in the market for close to 20 years. And they're both activated carbon based. So they both have an activated carbon platform. And depending on the technology, so for say Boss 100, it's got reactive iron impregnated within the activated carbon, or we can also add in electron acceptors or electron donors and bacteria as well to get a microbiological degradation component as well. So activated carbon obviously is a great sponge that we put in the subsurface. It adsorbs the contaminants, and then we load up these different treatment mechanisms depending on the site and depending on the application. Okay. And it is important, and we'll actually show a slide here in a minute. There's depending on the size of your particle, right? So the particles that we'll be talking about today range from a powdered to a granular size. And what's important to note is that there are smaller size particles out there, colloidal size particles, and they have applications, and every technology that we work with has a box that it fits in. And so depending on the site and geology, that may not be the best application. And so here's an example of a site in North America where this was a tight glacial till geology in North America. And you can see back in 2017, there were multiple injections. This was for a permeable reactive barrier at a petroleum site. And there were multiple applications of activated carbon, as well as an application of chemical oxidation. And you could see the data there on the y-axis is your BTEX and your PHC. And the data was really erratic, some increases, some decreases. And then we got involved in 2018, if you pan over to the right, and we did a proper characterization and application of the slurry in that tight geology, and we're able to install a proper PRB, and you can see the concentration decreases. And this was a redevelopment site, And so you could see by selecting the wrong technology here, actually delayed the redevelopment of this project. So, so Giorgio, I guess I'll go ahead and kick it back to you.
Thank you, Mike. And yeah, so where we came from, pretty much we have a few slides showing you just visually how things have developed over the years. So when we start, as Mike was saying, in 20 years ago, when RPI developed and patented the trap and treat products, you know, we started with basic, you could call it basic equipment at that time. And, you know, the early days issues that we encountered straight away, and that were the key focus in improving and providing a structure that then could be more replicable in terms of application, where how to maintain the slurry in suspension. When you deal with suspended slurries, it's not an easy thing to have maybe half of the volume of your tank filled with activated carbon and try to actually maintain that at the right density and try to inject it at high pressure and high flow. It's not an easy thing to do. You would have to transport that slurry from a mixed tank to an injection nozzle that could be located 100 meters away by the time your tip is positioned where you need to inject, and make sure that every single drop of slurry gets injected in the ground, because ultimately the client is paying for every single liter and kilo of slurry that gets injected. And also how to manage daylight. So the more sites we did, the more we learned about how to control daylight. And that led us to kind of come from a lot of experience and develop injection systems, which are now sort of, we call it top-notch in terms of safety features, application flexibility, mixing properties. All that is now combined with companies sitting over 5 continents and sharing experience, and everybody has learned something. So these are the systems used by Ejlskov at the moment. We have 5 systems in-house shared across 2 continents. And all it matters is that we are capable of truly providing what we put in the injection plan and transforming that plan into a site application that can be replicated over and over. So these systems are now guaranteeing the best amount of safety to the workers going around and to everybody that is involved in the project. So we have safety bypass valves because we are dealing with high pressures and high flow, mixing pumps that can handle 2,000, if not plus, because we have a 10,000 liter mixed tank of slurry that can be maintained at a homogeneous density, transferred to the injection pump safely, injected all the way into the ground without losing a single drop of product, as every single liter will transit through an injection hose all the way to the nozzle. And we will look into some extra details later on. When we go into the applications in the field, and again, the whole thing about safety and how we can apply this product maintaining active sites without losing their production or their clientele. So here is a couple of examples of gas stations where we could easily let the client continue their sales, and we were working within a small area assigned by the client at each site, and we were able to do all the mixing, all the preparation, deliver the injection products to the cart, down into the subsurface, and complying with all the regulations and all the requirements from the authorities and the client. And ultimately, then it goes down to the technicalities behind the applications. So when we look at the key to success, as Mike was explaining, it's a tight fit between the design and what we deliver on site. So when we look at the basis of the application, we normally work on triangular grid spacing that can go from 1 meter to, let's say, 2.5 meters, depending on the type of geology, the depth of the contamination, the amount of contamination that may be present. So if we have hotspots carrying a lot of contamination tight in soil, we may have to do very surgical injections to apply the product correctly. We always do top-down injections. That's the only way that you can apply the product the best way possible. By doing bottom-up, we will just keep injecting back in the bottom of your bottle. We advance about 0.5 meter, 60 centimeters at the time. We can play with the pressure settings and with the flow settings. So the systems we have available can go from 0 to 170 bar. That's not the pressure that you dissipate on the soil, but that's the pressure that it takes for the system to bring that slurry that can go from 10% by weight density to 50% by weight and deliver it homogeneously to the tip. And the same thing can vary with the exit velocity. So when we deal with different type of soils, you want to be able to adjust the exit velocity of your slurry. So when it comes to, for example, sandy formation, you need a lot more flow and a lot more exit velocity to be able to create turbulent mixing. Over the years, we have been sort of listening to feedback of people thinking that sand is an easy geology to inject into. It's actually probably the most complicated. Clay becomes almost easier to inject when you have the right equipment. So you got to follow pressure, flow and exit velocity, the volumes and the slurry density, how to play in the field with changes of management of change. There could be daylighting, there could be infrastructures that we didn't know about that we have to work around. So how to redistribute the points. So a lot of small things that have to be taken into account. And here is an example of how this real life application when it comes to injecting that flow and high pressure. We have also developed, and I would like Mike to explain a little bit more about that, the geotap pre-drill technique. And Mike, please go ahead and fill us in.
Sure, thank you. So geotap stands for Geologic Targeted Access Point, or geotap for short. And it's what we call a pre-drill technique. And so there are quite a few sites here in North America and Australia as well, where we've, and Europe, which I think Giorgio will touch base on here in a minute, where direct push by itself can't reach the design total depth. And so over the years, we've developed this technique where we use traditional drilling, so augers or sonic, to be able to advance down to whatever our target depth is. So if we get refusal at 10 meters and our design is 15, we'll auger or sonic down to 15. We backfill that with bentonite, let that hydrate really well, usually 24, 48 hours. And then we come back down through that with direct push. And because of the injection systems, and because we're injecting slurries, and that's a really important point, is that this technique works only with slurries, and you got to have the right injection system that to deliver the proper flow rate and pressure to be able to cut through that bentonite and get out into the native geology. And so if you looked at that video that Giorgio showed on the previous slide, it looks sort of like a pressure washer, what's coming out of that injection tip. And so you can imagine that slicing through the bentonite and getting out into that native material. And so we've done probably closer to 60 sites now around the world using this application technique for all of the slurry technologies that we work with.
And yeah, the example we have on this slide is from a site, for example, in Finland, where we had managed with not a few challenges to perform a remedial design event by doing direct push and going down with 2 different diameters of piping to be able to collect the samples that we needed. At this site, we took 425 soil samples. You could see the highly homogeneous sands that we had to go through, and with direct push is not that easy because you're trying to displace something that is highly compacted. So when it came to the remedial design, that was a good thing because we learned that we had to do something different from the injections. We had to reach about 18 meters to protect the groundwater, which was ultimately the goal of the remediation. The soil contamination was not deemed as a risk necessarily for vapor intrusion or anything like that, but the problem was protecting the contamination spreading in the groundwater aquifer. So at this site, we applied a sort of horizontal barrier. We performed about 150 drill points to depths between 16 and 18 meters by rotary percussion. We reintroduced bentonite in the bottle and then went down again with direct push. This site was completed in about a month. We achieved no further action a few months ago after proper monitoring was done. When it comes to bedrock again, Mike, would you like to share a few words?
Sure. Yeah. So we do less Well, I guess I should say we're doing more and more bedrock these days. I think a lot of the shallower overburden geologies have been remediated, and so here in the U.S. we're getting involved with more and more bedrock sites. And so bedrock is obviously a different application technique. We can't use direct push. We're using straddle packers, and so you'll see there the picture in the middle on the left is a picture of the custom packers that we have that we had made for us, and it's about a 0.6 meter interval between the inflated packer glands that you see. And so the key with bedrock, as with any site, is the characterization. And so we use that same packer set to be able to sample each individual fracture and then come back in and to be able to inject slurry through that. You can see the nozzle there actually on the picture on the right. Whenever the packer is inflated, you can see there that's where the product comes out. But key with anything is the characterization. So upfront geophysics and sampling of the fractures is going to be critical to success. And we don't have much on this. It's not really the focus of this presentation. We just have the one slide, but we do. AST has done several webinars that are specific to bedrock. And so if you're interested, those are posted on our website, and Giorgio can provide that information to you. Here's just some maps of the states in the US and the countries where we've done the various application techniques of geotap up in the upper left and bedrock in the lower right.
Yes, and to continue, we have a few final slides to show regarding what we collect also in terms of field data to confirm that application has been positive and according to what we were expecting. So the distribution of the slurries in the subsurface is, regardless of what people may say, it's as predictable as possible when it comes to knowing what you're doing with your injection system, but you still have to go out sometimes and check. So here we have a few examples of different soil types, so from sands to silty sands, gravels, and different type of slurries. So this was a powdered activated carbon Boss 200 product applied. This was a Boss 100 product applied. And this is actually an ice core from Denmark, where we had a very tough clay to work with. And here we have a transition zone that shows exactly that difference in spreading depending on how you distribute your product. And here we can see clearly the difference in distribution of the product when it comes to gravels and sands, where you have that sort of turbulent mixing, compared to managed to enter Danish clay, especially in the Copenhagen area, which is extremely hard. And you can see the distribution looking more like a tree root, but still creating, as Mike was mentioning at the very beginning, this sort of sponge effect where you try to draw your contamination on and then eventually treat it. And moving on with our information, we will use a few minutes about daylighting, for example. That is another big topic when it comes to discussing how can we prove that injections are successful and what happens when we do have daylighting. So daylighting is something that we got to live with. It's going to happen. I think I've only done one site so far over the last 10 years where every single point delivered without a single event of daylighting. Any other site, you may count a few daylighting events. It's how to control them and how to evaluate them. And these are pictures, examples that can tell you also that it's something that is already there on site as a pathway. You just got to find it. So here you had a monitoring well that was daylighting only from the outside. How can you have fluids only exposing themselves from the outside of a well and not from the inside? So it means that somewhere the borehole has not been sealed properly. Here it's me personally extracting a 15-meter well from a borehole in Finland. How would you do that if it's not because the borehole hasn't been sealed? And here, similarly, in Copenhagen clay, a 10-meter deep borehole, 90-millimeter wide, it has left open. So you got to play with that kind of information, and you need to understand how to address that, because it's not every single injection point that counts or every single injection interval. Is the complexity and the total amount of points that you're doing that require understanding when you are in the field, and how to manage that change and apply the product properly based on the CSM, the targets that you have to achieve, the criteria that authorities and client may have put in place. So it's a lot of experience that come into that. The other thing that we do to make sure that clients and authorities can come back and ask us any questions about what have we been doing at the site is that we track and record every single injection points. We have a dedicated set of tablets where we plug in all the plan of the injection, and then we just record the information as every injection point is done. We record all the informations about pressure, volume that has been injected, has there been daylighting, has there been refusal, how much product has been injected compared to plan, and based on that, we can create a final as-built injection model that shows clients and authorities this is where we have injected, this is where we did not inject because of infrastructures or something that was in the way, and how it compares to the initial plan that we had in mind. And most importantly, we can also do soil mixing as well, which is not something to cross off completely, still a very useful way of applying the product. Here is a site in Finland where we did a high resolution remedial characterization, remedial design, where we established that it was easier to stockpile clean soil that was present in the top 2 meters, and then advancing layers and blending the product with a bucket excavator. And the good thing is that we can go back again and trace what we did. These are cores that are actually very fresh. They are only 2 weeks ago that we did the validation. And you can see the difference of how the product gets distributed in the formation compared to an injection. And this also becomes the best way of applying a product if you are able to do so, because you can see how much better contact you can have between the formation, your product, and how that biological treatment can occur a lot faster and a lot better. And I'll leave Mike again a couple of minutes before leading into the Q&A session to describe a bit what we have learned also about PFAS remediation and what we use for that.
Sure. Thank you, Giorgio. So everything that we've discussed thus far has really been the activated carbon-based products, but really these injection systems and techniques can be used for other slurries as well. And activated carbon is not always the best option for in situ applications due to the nature of PFAS and its the likelihood that it's going to ultimately get discharged off of the activated carbon. And so we've got involved with Setco, based here in the US, who have developed a modified clay product that absorbs PFAS better and longer than activated carbon. And so we entered in an agreement, just like similar to what we have with RPI, and Ejlskov is part of that as well, to be able to offer Fluorosorb is the name of the technology that gets slurried. And you'll see there, we did some product testing at our headquarters in the United States in the upper left there. You can see the product being mixed in the mix tank. You can see there with the nitrile glove what it looks like. So it's a modified clay, so it doesn't swell. It goes in as a granular material similar to activated carbon. And it can also be soil mixed in. As Giorgio mentioned, that's best way to really apply any technology, not always an option for us, but if you can ever direct mix anything in, that's always the preferred approach. And what you see down there in the bottom left, that's an in situ stabilization project where they were adding a certain percentage of cement as well as Fluorosorb to bind up and lock the PFAS contaminated soil.
Well, thank you, Mike, and thank you for all the attendees to have had the patience to listen to us. I can see we have a couple of questions that popped out in the box, and as I mentioned, you're more than welcome to submit any question in the Q&A box. Just place the mouse all the way down in your screen and you should get this Q&A chat box to appear. One comment, it's not really a question, Mike, we will follow up by submitting information about the US bedrock applications. One of the attendees is asking for that.
Absolutely, yeah, for sure.
We'll follow that. We have a question that states, what are the potential risks or side effects of the treatment? Are there any potential risks or negative impacts associated with the treatment? Example, possibility of residual contaminants, changes in soil fertility, or any other concerns related to long-term effects of the treatment. Mike, would you like to take that, or?
Sure. So the treatment mechanisms that we use are all traditional treatment mechanisms that have been used for, say, 20 to 30 years, right? So, for example, in the iron impregnated within the activated carbon is very similar to zero-valent iron chemistry, or we're adding electron donors like starch, for example, where you're getting reductive dechlorination, or we're adding electron acceptors like nitrate and sulfate for anaerobic degradation of petroleum hydrocarbons. And so any effect that you would have where, say, I'll use BOSS 200 as an example on a petroleum hydrocarbon site, you're going to have on a temporary basis elevated sulfate levels, for example. But in our experience, that stays within the treatment zone. But if you did have a site, for example, that was immediately adjacent to a drinking water well or a sensitive receptor like a creek or a stream, then that would change our design to make sure that we were staying sufficiently far away from that from that receptor. But that effect is only for a relatively short period of time. And then there really aren't any issues with soil fertility. Actually, the nitrate and the nutrients that we add as part of, say, BOSS 200 are similar to what you would find in soil fertilizer, actually. So, and everything, I guess I'll just finish up on this, Giorgio, if you want to add anything. All the products that we apply in the subsurface are food grade.
I'll continue. There was a question coming up regarding, is the remedial product always or almost always disposed of via hydraulic fracturing? Is there any other way to propagate the remedial product? We wouldn't call it hydraulic fracturing per se. So the pressure ratings that we showed, as I said, it's the pressure you need to get the slurry from the mixed tank to those small nozzles and be able to create that blasting effect that we saw in the clip, which means that the energy that we actually propagate on the soil, even in clay formations, you may be looking at anything that varies between 2 and 5 bars. We can see that from our pressure gauges mounted on the system. And the rest is baseline pressure that we build up from the pump, pushing through 2 or 1 inch hydraulic hoses, and then ultimately having to push out of 5 or 6 small nozzles that are 3 to 6 sometimes millimeter in diameter. So ultimately, I would say it's more like I wouldn't call it fracturing. I don't know, Mike, which word you would use, but I think it's a bit overkill maybe as a terminology.
Yeah, so I mean, I would say traditionally hydraulic fracturing is at least how it's the term used here in the US in general. It's for large where you're on very wide spacing, very high volumes, very high pressures.
Yeah.
So it's very much like scaled down from, say, oil and gas applications.
Yeah.
What we're doing, like Giorgio said, is on a much tighter grid, much lower volume, much lower pressures. It's lower pressure than you would think. And when you're in a sandy formation, that's more of a fluidization there. So that fracturing really wouldn't apply. But these technologies cannot be applied, for example, through injection wells. That we wouldn't be able to do. It has to be applied under at least some pressure through a jetting nozzle, similar to what Giorgio had shown earlier.
All right. Mike, I know you're running against the deadline, so we'll let you. I'll take it on. The last question, at least that I see popping out at the moment, is regarding how cost effective the treatment is. The simple answer is, in general, we see as being 20 to 50% cheaper than traditional methods that you can list out as excavation, pump and treat, mechanical treatment kind of solutions. Then again, it depends on the site complexity and how much contamination you have on site. But ultimately, from a sustainability standpoint, we can see that over the years in our, let's say, geographical range of where we operate, there is more and more attention to try to avoid disposing soil off site, because it's just taking problem from site A and moving it into a landfill. But ultimately, the big problem is when it comes to redevelopers or people that clients that need access to their land as fast as possible, leaving a treatment system in place for years with extraction wells or any sort of infrastructure that is left on site may slow down the process. So this type of treatment become time effective as well, because once they are installed and they are designed properly, they can be left in the ground, and the bacteria and the activated carbon and all the nutrients will continue working for as long as needed. And that's what makes our, let's say, solution as effective as possible. So we are now at the half an hour